So good afternoon, everyone, and welcome to the UnifyFS tutorial. I am Michael Grimm. I will be presenting alongside Cameron Stanovich. UnifyFS is a project within the EXA-IO ECP project. We're grouped together with the EXA HDF5 project. The UnifyFS project has contributions over its lifetime from Lawrence Livermore and Oak Ridge National Laboratories and NCSA. The current team is listed at the bottom with PIs Catherine Moore from Livermore and Sark Worrell from Oak Ridge. Next slide. So what is UnifyFS for anyone who hasn't come across it before? So basically, it's an ephemeral user-level shared file system for burst buffers. And in the next few slides, I'll get into the type of burst buffers I'm talking about, because burst buffer can mean many things to many people. But the overall goal of our project is to make using burst buffers on exascale systems as easy as using the existing parallel file systems, with the added benefit of taking advantage of the consistent performance behaviors to make your I/O that much faster as well. So the real goal here is it should be as easy as just replacing all your paths for files that you want to put on burst buffers with our /UnifyFS prefix instead of whatever path you use on the parallel file system. I mean, that's as easy as it gets. Basically, you could treat UnifyFS as just another parallel file system. Next slide. So let's get a little bit into the history of HPC storage architectures and why burst buffers have come into existence before talking about which types of burst buffers we're targeting with UnifyFS. So on this slide, we're showing a typical HPC storage architecture where you have some set of compute nodes in an HPC system connected via the HPC network to a set of essentially router nodes that take traffic from the compute network and go to a dedicated storage network, which houses the parallel file system. These intermediate nodes may be called I/O nodes or I/O routers, depending on what system you're on. But this is a pretty typical layout from starting 10, 15 years ago to even today. Now, this architecture has many potential sources of I/O bottlenecks, which are highlighted here in these boxes. So first, at the top of the figure, we have contention on the HPC system network, where traffic on that network can contend with your I/O traffic that's passing over to the I/O storage network. Now, some systems have dedicated compute like MPI networks versus I/O storage networks. And so you're either seeing contention from just the I/O traffic or contention from both I/O traffic and normal parallel application communication. Once we get down into the I/O storage fabric, you start seeing contention from other shared file system resources, such as the I/O nodes themselves or metadata and storage servers within the file system. Now, due to the cost of deploying large-scale parallel file systems, what often ends up being the case is you'll have one very large thing that is actually shared by multiple compute systems. And so you also see contention for using the parallel file system from other clusters. And then finally, historically, parallel file systems have tried to provide general purpose file system semantics, which is good because it promotes ease of use. People are familiar with it. But unfortunately, it also results in the parallel file system having to implement some fairly costly locking and synchronization mechanisms that only have a negative effect the more and more you scale up the size of the system. Now, we have all these possible bottlenecks, and things are only getting worse. So the size of our HPC systems are increasing. The number of systems we're connecting to these things is increasing, and our workloads are becoming more and more data intensive. And so this has brought about the need for things like burst buffers, because it's no longer reasonable to expect the parallel file system to be the one and only thing that services all your I/O traffic needs for your data center. Next slide. So as a result, we're adding burst buffers, and the HPC storage architectures are becoming more complex. So on the left here, there's the local burst buffer model, and on the right, we have the shared burst buffer model. So in these figures, you can think of each one of those little heat map of boxes as a set of processing elements. And in local burst buffers, what we do is we associate one or more storage devices with each set of processing elements. And those processing elements may be a node, a single compute node, or it could even be a rack of compute nodes, for example. This is in contrast to the shared model, where you don't keep your storage devices within your compute systems. It's actually basically another tier in the storage hierarchy. And you typically allocate those shared resources on a job level allocation strategy. Now, in the future, we expect that things are going to become even more complex and may combine both of these models within the same. Now, each one of these models has different pros and cons. Next slide. So for local burst buffers, one of the key advantages is you're only seeing local traffic, and that leads to pretty consistent, repeatable performance, and also mostly avoiding contention. So the only contention is the processes local to that storage device that are also accessing the device. It also has the potential for great scaling behavior, because essentially the more compute you allocate, the more storage you get. On the bad side is, well, local burst buffers only provide a local storage namespace. So, processes on one local area cannot see data written by another local area. And that hurts traditional parallel I/O, where everyone's going into one to a shared file. It also hurts producer-consumer workloads. So in contrast, the shared burst buffer model does provide a shared namespace, so it solves some of the bad issues with local storage or local burst buffers. And so it's easy for applications to adopt. The downsides are it may not be quite as fast as the consistent, repeatable behavior of node local storage. And it is a shared resource. And so you may see contention still, either coming from the compute nodes to the shared burst buffer, or also from multiple jobs sending data from the shared burst buffer to the parallel file system. So UnifyFS is really targeting the local burst buffer model. And so we want to keep all the good, the fast behavior, the no contention, the good scaling, but address the sharing. So make it easy to use shared file abstraction with local burst buffers. Next. So again, the problem is that sharing on local storage is not natively supported. And so our goal is to provide a shared namespace, next, over these node local devices or near node local devices, such that you can share files easily and you can have fast I/O. So we make it easy by presenting a shared namespace across these distributed independent storage devices, and also by making it easy to integrate within existing applications. So in most cases, you don't actually have to change your application to use UnifyFS. Any application that's already using an I/O middleware library or I/O library like MPI-IO, HDF5, AUDIOS, etc., or a checkpointing library like OLCF, the use of UnifyFS is basically seamless. We also provide an API that can be used by applications or IO middleware for tight integrations, but primarily it's a seamless integration into applications. And UnifyFS is fast. It's tailored for the workloads that we see on HPC systems, which are things like checkpoint restart or visualization output, where you have basically bursty phases of IO. UnifyFS is a single job file system. You start it up at the beginning of your job, you tear it down at the end of your job, and because you're using no local resources, you see limited contention from other IO on the system. And finally, we can use a combination of both memory-backed and file-backed storage, which can actually further improve how fast your IO is. So next slide. So at a high level, UnifyFS looks kind of like this. So based in a stack, in your storage software stack. So at the top level, we have integration with user jobs. So UnifyFS provides a command line utility that allows you to dynamically set up and tear down your UnifyFS file system within your job. And then once you link with the UnifyFS library, your applications can do what they normally do. So we support both end-to-one shared files, end-to-end, which is file per process. We support collective IO with scientific IO libraries. In the stack, we sit underneath all the existing IO middleware libraries or the checkpoint restart libraries. So UnifyFS uses Gotcha for IO interception, which allows us to dynamically hook in at the lowest level and see all the calls. And then we can translate those calls to operations on local devices. Additionally, we provide an API or other utilities for moving data into and out of UnifyFS to and from the parallel file system. And we also have semantics for laminating files. And I'll actually talk about some more semantics we have in a little bit. Next. So here's some recent performance information on UnifyFS for the Summit system at the Oak Ridge Leadership Computing Facility. So this is running a recent version of the IOR benchmark, which is commonly used to benchmark IO performance. And in this case, we're comparing IOR read and write on UnifyFS versus using the existing parallel file system, which in this case is Alpine, and it's a GPFS, or also known as Spectrum Scale, and its rebranding. And so in this case, we've configured Unify to only use the node local NVMe drives in the Summit compute nodes. And so each one of those drives provides roughly 2 gigabytes of peak write bandwidth and 5 gigabytes of peak read bandwidth. And in the top graph, you'll see the PFS lines or the parallel file system lines and the UnifyFS ones. And we've compared IO performance using POSIX IO, MPI-IO, which is independent IO, and MPI-IO, which is collective IO. And what you'll see is, at small scales, obviously, you don't see much benefit over the parallel file system. In fact, the parallel file system does better. But once you get to a relatively small size and compared to the size of Summit overall, UnifyFS, the good scaling performance, starts to really pay off. And even though Alpine performance kind of trails off there at the end, levels out, we continue to see roughly linear scaling for increasing number of nodes. Now, in the bottom graph, we show the same data for the read case, and things aren't so rosy there because primarily GPFS is really good at caching. And so if you're reading back data you just wrote, it does a really good job of that. So in this graph, you can see that UnifyFS doesn't really provide any benefit at up to 512 nodes for read workloads. But the thing to notice here is, so each one of these bars has the kind of the standard deviation bars on it. And if you look at both the write and the read results, you'll see that the parallel file system has much more inconsistent behavior. So the error bars are much wider on the parallel file system, whereas UnifyFS still provides very good consistent behavior. All right, next slide. So I mentioned this before, but one of the key advantages of UnifyFS is we can actually customize the behavior of the file system to meet what your application needs are. Now, by default, we make some simplifying assumptions about how you access your data. And these assumptions are common to most HPC I/O workloads like checkpointing or producer consumer. And this basically means that your I/O occurs in phases, except in limited circumstances. Basically, if a process is reading back the data that it wrote, and no two processes write to the same file offset concurrently. And this is fairly typical because most applications are doing large scientific data arrays and matrices where they're writing their own pieces. And without any explicit synchronization, the processes can't see updates written by other processes. And this is completely, these default semantics that we have are compatible with standard MPI-IO behavior and the behavior of HDF5 and its parallel independent mode. Now, we can tune how we behave, and you can see more at our read the docs site. But one of the key things is if you want POSIX style consistency, or if you want compatibility with HDF5 parallel collective I/O, we have a mode that you can enable with an environment variable. You can turn on client write sync mode, which is basically perform a synchronization operation after every write. Now, this will impact performance because it has a lot of synchronization, but it will be functionally and semantically correct. Now, I mentioned this briefly before, but one of the key semantics that we actually offer is when you're done with a file, you can laminate it. And this makes a file read-only, and it synchronizes all your file metadata across all the nodes in your job. And what this really means is any process on any node can read the entire file, any part of it, and it's reduced cost for doing those reads because of the synchronized metadata. So next slide. So here we've rerun some of our IOR read performance numbers to highlight the different behavior you can see when you enable different types of UnifyFS semantics. And here we're playing around with the different configurations for how we do metadata caching for the file extents that you wrote. And the first thing we do is default mode, which is basically we don't do any metadata caching. We have a server who's responsible for keeping the metadata, the global metadata view for everyone. And when you do a read, that read request is forwarded to that server to figure out where the data lives, and then we read the data from the server where the node was written. The second case is default with lamination. So this means, we've already laminated the file, so we've done this broadcast of our metadata, and so when you do a read, the local service has that metadata and doesn't have to contact anybody else to figure out where to go read the data from. The third case is server local metadata caching. And this means that for all data written local to a given server, regardless of how many client processes are on that server, we can cache that metadata and basically shortcut read requests such that when you look up a particular data, and if that data is local, we can immediately read that data and return it to the client without talking to the person who's responsible for keeping the global view. And finally, and this is the most limited of the options, is client local. So this mode is only useful if you know for a fact that no two application processes will ever write to the same byte offset throughout the lifetime of the application. But in this case, inside the application client library, we can cache that metadata. And so basically client reads are serviced within the client application space. We don't even have to go to the local UnifyFS server. And so in the top graph here, the takeaway is twofold. So one is client caching is really good when you can do it. But as I said, it's only useful in very limited circumstances. But if you can, you get great performance and great scaling. The second is, so figure A here is reading back data that was written locally. So all the data should be stored on the local storage device, and that means that the local server knows about it. So in this case, server caching and laminated behavior is basically identical. And it improves performance versus our default, which has to go and talk to this centralized owner of the metadata. Now, the bottom graph shows the results when we turn on the reordered reads option for IOR. And this is basically says that rank n+1 will be the one who reads the data written by rank n. And so this means that for how we've deployed it on Summit, where the ranks are packed within Summit compute nodes, so we have 6 processes per node. So 1 out of every 6 will be doing an off-node data access. And here we see that the default case and the server case are basically the same, because what happens is your read bandwidth is limited by the slowest case, which is the off-node read, regardless of the metadata lookup. But here's where lamination really helps out, because once you've laminated the file and you have all the metadata at every server, you can get a fairly substantial read improvement from having that and not having to query the metadata remotely. All right, next slide. So I mentioned this before, but UnifyFS is compatible with most I/O middleware. So in particular, it works with HDF5 as well as other I/O libraries, but we actually test HDF5 the most because we're partnered with them in XIO. So we've taken the HDF5 test suite and we run the tests using UnifyFS as the destination. And we're slowly working through the cases that we don't cover, but for the majority of the tests, we function correctly. So next. And basically the only thing you do is you change the file path that you use for your file open call. Build and run your application, change file paths. This is the same story for almost all uses of Unify. Next. So here's an example of a HDF5 application that we've tested with on Summit again. And here, we're actually showing an evolution of a performance study we've done. We actually started this study on the FlashX astrophysics code over a year ago, before the last ECP annual meeting. And so FlashX has a I/O benchmark configuration called FlashIO that we're using. And in that configuration, basically it aligns the compute part of the application and just does the I/O. And it writes roughly 72 gigabytes of checkpoint data per node and 220 megabytes of plot data. And here, again, we're comparing UnifyFS against a parallel file system with different versions of HDF5 and with a original application and a tuned application. So for the versions of HDF5, 110.7 is currently the default if you log into Summit and just module load HDF5. Whereas 112.1 is a more recent version that has some improvements that were suggested by the HDF5 team. And we were actually working on this performance study in collaboration with the HDF5 team. So the tuning was, so back when we very first ran this, we noticed that neither the parallel file system nor UnifyFS was providing the kind of I/O performance that we expected to see. And so that's that first PFS-1.10.7 line. And so you get to about 30 nodes and it falls off, and that's nowhere close to the behavior that you should see with a parallel file system. So we studied the application using the Darshan IO tool, as well as the recorder IO profiling tool. And what we found was a couple of things. So one is the IO code in Flash seems to have been written quite a long time ago with not very much attention. So the best guess from the application developers is it was probably written around the same time that HDF5 was first released. And so we found a redundant call to H5F flush that occurred after every single write operation in the application. And this was clearly visible because when we looked at the number of calls to certain synchronization operations, it was very, very high. And if you looked at the trace view of it, you could see everything was stalling with these synchronizations. And so we eliminated that because it was redundant and not necessary. And then we also took a known good MPI-IO configuration for Alpine and applied that. And so you'll see that just by tuning the application, we restored reasonable behavior. So it scales up pretty well to 64 nodes and then starts dropping off again. And then at the suggestion of HDF5 team, we said, okay, so let's see if the recent improvements have helped things at all. And at smaller scales, you get a little boost, and then at 128 nodes, we see a pretty big jump there as well from just using a more recent HDF5. And then finally, we took that tuned version, that most recent version of HDF5, and then we targeted UnifyFS instead of the parallel file system. And what we see is pretty good results. We get a 2 to 3 times the performance with UnifyFS versus running on the parallel file system. All right, next. So can I use UnifyFS with checkpoint restart libraries like Veloci, which is another ECP project? Yes, of course you can. So if you start with your existing application, which has a nice checkpoint function, and you're using the file-based method, so you see the Veloci route file method. So new file here is the first level storage location that you want to route the file to. Next. And basically, you change the value of new file, which is some string, which is not defined in this code here, just to point to /UnifyFS, similar to how we did for the HDF5 example. And that's the only change. And if you're lucky, all of this stuff is specified outside your application code. It's either an input parameter or a configuration file, and you actually don't even have to change your source code. And with that, we'll move over to Cameron to do the tutorial portion.
Thanks, Mike. So I'm Cameron, and again, if anybody has questions as we go, feel free to put them in chat or chime in. We're flexible. So assuming everyone can hear me, I'm going to go a little bit more over a bit more in depth on using UnifyFS, how to access it, how to integrate it with your application, any changes that will need to happen, what any changes need to happen to running your job, as well as some environment of UnifyFS that you can use to tune to your IO needs. And finally, getting any data in and out of UnifyFS that you may want to persist. So essentially, if you are working on Summit, we do already have a pre 1.0 release installed with a few compilers there. And by pre 1.0, I mean a snapshot of our develop branch at a point that's newer than our latest release, with some improvements, as our 1.0 release is not quite there yet, but it's coming soon. So on Summit, you just need to module load that, or module use that UnifyFS module file, and then it is available for module avail, and then you can just load the version and compiler that you would like to use. This is using an MPI mount, I believe, for all of the versions installed there, and I can touch a little bit more on what that is. If you don't want to use that version or you're on a different system, we recommend going through SPAC to install and load UnifyFS. And we offer a few variants, build time configurations. And the main one I'll touch on is that auto mount, which I realized in the last slide. Sometimes we seem to interchange MPI mount and auto mount, but they are the same thing here. And what that enables is for UnifyFS to mount and unmount during MPI init and finalize. Again, I'll go, there'll be a little more detail later as to advantages for that too. And then we have some 4chan support, and then PMI-X is for bootstrapping. And then if those that not so familiar with SPAC, you can install with any or not use any of these variants should you choose to. If you can't use SPAC or choose not to, we are open source on GitHub. You can grab our latest release or clone UnifyFS from there. The address is at the bottom of all these slides, so you can grab it if you need. Doing so, though, you'll need to handle installing all the dependencies, which is always a fun activity. We do have a few here. Mike mentioned Gotcha earlier, which is an LNL project. We use Margo for communication, which has quite a few dependencies itself. And SPath is an optional dependency for normalizing relative paths. We do provide a bootstrap script that can do all these, download and install these dependencies for you. That sometimes it might be a little more tweaked for developers, but you're more than welcome to use it. And then to build and install UnifyFS manually, we use AutoTools. Margo uses a package config path that you'll need to export and then simply configure with the options that you choose and with the paths to Gotcha and SPath here, and then just to make install. All right, once you're built, and if you need any help with that, just reach out. You just modifying your application, as Mike touched on quite a bit. Here's a simple MPI program that's just opening a file on Lustre and just writing hello world from each MPI rink. And as Mike said, just change the path to UnifyFS. Is really all you need to do. And then here we are taking advantage of that laminate optimization that Mike mentioned for optimizing our metadata. And in this case, we've you notice we don't have an import of UnifyFS.h here. There's no API calls in this. So we have when UnifyFS or when Gotcha essentially intercepts a change mod for read only, we can interpret that as a form of lamination. We do, although also offer a UnifyFS laminate API as well as a command line utility. And we're looking into use cases for laminate on close or unmount if there is a need for those. Also, though, if you are not using MPI or want to use API calls, you can then include the header file and access the UnifyFS mount and unmount. So this is the case where the auto mount or MPI mount configure is not enabled. And you'll need to make those mount and unmount calls yourself. Here again, we're still changing the path to UnifyFS and then also still just using change mod as a laminate, but in this case, we could also use the UnifyFS laminate API call. Once your application changes, as possibly as few as one, if any, need to happen, you then need to link with UnifyFS. We do offer static linking with some limitations, but we do have a config script to make sure you get all the flags you need for that. But we do recommend dynamic linking, for which we use the Gotcha library. And here you'll just need to link with the UnifyFS MPI Gotcha library, I believe in that case, to take advantage of the MPI mount feature. A little bit of what Gotcha does. Probably don't need to go much detail here really, but essentially your application, if you're at some point when you're opening a file, the location of that function, in glibc in this case, the symbol is looked up, it's carried, or it's located in the global offset table here, where it's looked up and that pointer is followed to glibc, where that function is then executed. And essentially what gotcha is doing that allows us to intercept at this lowest level is it's replacing the locations here on the right in the global offset table of where those functions are located, essentially our UnifyFS wrappers. So when your application is calling fopen here, it gets redirected to UnifyFS for our processing. And in the case that you're not writing to UnifyFS, so essentially if you do want to use UnifyFS, you're not restricted only to it still. You can still write to the parallel file system. We'll just pass on anything not directed to us to the original call. All right, once you're linked, you're ready to get running. You might need to do some configuration of UnifyFS to tune to your application I/O needs. And this is also kind of a big part of where we want your help, want users to help us figure out what use cases there are, what kind of tuning we can do to help UnifyFS be faster and better for you. These configurations can be done through a configuration file. Environment variables are probably the easiest way to go. We do offer some with our command line utility as well. And there's a whole list of them in our documentation there. But a simple example of a configuration file, here we're setting what our mount point is as /UnifyFS, but call it what you want. We are turning on some logging here and designating where those logs are going to go. And then this here at the bottom, the very bottom, the spill directory is essentially the main one we need from users, which is you're just telling us where, essentially the path to your burst buffer, your node local storage, where you want the data to live. And UnifyFS will it will manage memory, or it will manage data in memory first because it's faster. But here you can also customize how much, if any, of shared memory you want to use. Essentially how big you want your file system, your user level file system to be in this case. All right, in order to get your job running now, we have a simple example here of running on 8 nodes. You can see our 8 yellow circles here at the bottom representing our nodes, with our cylinders representing the burst buffers or the node local storage for each of those nodes. Once you, for modifying your batch script here, you'll need to start UnifyFS to get the servers going. And here we're needing a shared directory path for bootstrapping. Currently, it's usually used as a backup in case like PMIX fails, but it's part of our bootstrapping thing here, where the servers will start up on each node. And once they've communicated, as Mike showed earlier, we'll have this shared namespace across your entire job. At that point, you can simply run your application as normal, and we'll intercept and handle your I/O. I don't have a slide for this, but something I could point out here too is like a producer-consumer workflow case here. You can imagine these first 4 nodes on the left being data you're producing, and then simultaneously consuming that data with another application or something here with the 4 nodes on the right, all of them with access to that shared namespace across the burst buffer. Once you're done, you just add a UnifyFS terminate to your script, and UnifyFS will clean itself up and tear down. Something kind of important though, you might want to persist any data that you create in UnifyFS. You might want to bring data you already have into UnifyFS. We do have API UnifyFS transfer calls that you can do source and destination both ways here. We do offer a command line utility, UnifyFS stage, that takes a manifest file, as well as the start and terminate commands have stage in and stage out options. And the manifest file here is simply just sources, or destination, source and destination, essentially. So that's pretty much the whole tutorial. Feel free to ask any questions. I will make a plug here, as Mike mentioned earlier, that recorder tracing tool that is being actively developed by Chen from UIUC. And it's been really nice for being able to see that whole IO stack of calls from HDF5 all the way down to POSIX. And inside Recorder, we're currently working with Chen to develop a tool called Verify-IO that takes these recorder traces, and you can essentially tell it what the underlying file system semantics are and what synchronization methods you're using as far as MPI. And in the case of UnifyFS, we're using what's called commit semantics here. And you can run a trace of your code through this, and it can basically use it to tell you if you're compatible with UnifyFS, or if not, we can figure out why or what kind of optimizations you could even use for UnifyFS. So feel free to reach out. We're working with this. We can definitely help you use this as a way to determine if UnifyFS is a good tool for you as well. So yeah, we need your support. We need your help. We need early users. We have those releases on Summit, but also we are planning a next release for this summer of an official 1.0 release. So you can find us on GitHub. You can find all of our documentation. Don't hesitate to ping us, to ask us questions, to get help running whatever you need. At that point, yeah, we got some time, so we're happy to dive into anything. We're happy to take any questions. I think Mike's been answering some in the chat here.
So I'll just take that one live. So no, we haven't tried any of the new Vol connectors in HDF5, but I would be interested to see. So I don't know that we would be compatible for the caching Vol, but I think we could probably work with the async Vol. And the logging one probably as well. But again, we need it. We've done the basic testing using the parallel and serial paths that go through the standard VFD.
Yeah, it would just be interesting to see how they all work in combination.
Yeah, I have a feeling that it might just happily work, but we would have to test it.
Yeah, I mean, if there's weird bugs or anything like that, we'd like to know about that. But also too, I mean, everybody's showing these really impressive gains, and it'd be interesting to see how well all that synergizes together.
Yes, Tom. So our UnifyFS start has a manifest file you can pass to it to stage in. Now, I will note that may not necessarily get you a data distribution that you like. So if there are suggestions on, what options we should provide for how to distribute data when we stage in, I'd be happy to hear those. So currently we don't support directories. It's just simple pairs of source file and destination file. The biggest catch right now is we don't really keep directory hierarchy information in the metadata that we use. We just have a full file path that's hashed to a key that we use internally. So for subfiles, I don't know how subfiles are represented. This is HDF5, right? I mean, I think it should just, anything that HDF5 does should work.
Hey, this is Rob with Marga. There's only a few participants here, so I'll hijack this a little bit. You didn't talk about the Unify client API, which I liked a lot. Is that still something you're supporting, or has that been sort of ignored in favor of these other approaches?
So it's not being ignored. So it's primarily directed at expert users such as yourself that are helping us integrate with other IO libraries. So the API is available. It's more than just mount and unmount. It's provides, asynchronous read and write, batched operations, explicit stuff. But for most applications, and we would really like them to be able to just use the code they already have and see if we can tune some behavior settings to give them good performance.
There's a whole section in the documentation, if you want to go there, that does cover that API layer.
And 1.0 release will be the first one where we officially announce that client API. So.
Also, if you have more questions come up while you're thinking about it, we do have a poster tomorrow. You can also swing by and ask questions too. All right, well, I'm happy to stick around if more questions come up, but looks like we might need to add some more content next time.
I thought I was going slow and I thought you went fast.
I probably went
it would all
fast.
just
Yeah.
average out. But. Yeah, maybe we do need that hands-on.
We'll work on that.
It's a whole week of Zoom. You give everybody 5 minutes to go get a coffee and stare at the window for a little while.
That's true. If we were in person, you'd have the time between now and your next meeting. So
don't feel bad. It'd be great.
All right, I think at this point we'll stop the recording, but we'll monitor the chat for the next 5 minutes or so.